I'm exploring how the number of neighbors considered in the k-nearest neighbors graph impacts the final embedding produced by the spectral embedding algorithm. The KNN graph is a crucial part of spectral embedding. Changing the number of neighbors changes how the algorithm sees the data's relationships. This directly affects the outcome. Increasing the number of neighbors considered creates a denser connection between data points. Imagine a social network. More connections mean the network's overall structure becomes clearer. Similarly, spectral embedding sees a clearer, more global pattern when more connections exist. This means a smoother embedding where distant points are better related. It's like seeing the forest instead of just the trees. When I decrease the number of neighbors, the algorithm needs to calculate the distances to fewer points for each data point. However, it has to make these calculations for every data point, resulting in many more calculations overall, because the process repeats many times. Think of finding the closest friends in a large group. The fewer friends you look for, the more people you'll have to compare to find them. Even if the data is easy to separate into groups with a straight line, spectral embedding builds a graph to find the data's underlying structure. The structure of this graph significantly depends on the number of neighbors. Therefore, changing this parameter still affects the result, even with linearly separable data. It's like building a roadmap. Even if the destination is obvious, the route details will still depend on many factors. This is the title of the problem, highlighting the core concept of the quiz: how changing the number of neighbors affects the result of spectral embedding. I am asked to select the correct statements on this topic. This instruction tells me that multiple options might be correct, prompting me to carefully evaluate each statement. I need to determine which choices accurately explain how changing the number of neighbors in spectral embedding impacts the outcome. This phrase simply means, how does changing the n_neighbors parameter, which controls how many nearby data points are considered, affect the results of a spectral embedding algorithm? It's a core question of the problem. Think of it like this: n_neighbors determines the scope of connections in our data, influencing how the algorithm sees relationships between data points. This is the main question, right? We need to determine which statements correctly explain how changes to n_neighbors affect spectral embedding results. The quiz tests your understanding of how this parameter changes the connections within a dataset and its impact on the algorithm's output. I disagree with this statement. Even if your data is already easily separated by a line, the algorithm still builds connections, or lack thereof, based on n_neighbors. These connections influence how the algorithm creates the lower dimensional representation, not just the simple linear separation. The underlying structure matters. This is generally false. If I decrease n_neighbors, I'm considering fewer neighbors per data point. This means fewer distance calculations, hence lower computational costs. So, this statement is not accurate. I disagree. While it does impact local neighborhoods significantly, I believe that influencing local connections strongly impacts the global structure as well. Think of it like a social network. Changing local connections within small groups will eventually affect the overall network structure. I agree with this. A larger n_neighbors means more connections are considered. This results in a more connected representation in the lower dimensional space, a smoother embedding with a better representation of global relationships. This question asks you to think about how changing the number of neighbors considered in the spectral embedding algorithm affects the results. It's all about understanding the algorithm's behavior and the role of the n_neighbors parameter. I'll explain this one. Imagine you are building a network of friends. A larger n_neighbors value means each person considers more people as friends. The network becomes denser, and distant people are indirectly connected through shared friends. The same thing happens with the data. A smoother embedding means the data points are more connected and the overall structure is clearer. Think about finding nearest neighbors again. With a smaller n_neighbors I still need to calculate the distance from each point to all other points to find the closest ones. That's a lot more calculations for each point. This leads to increased computation. The opposite is true for larger values of n_neighbors. This is partially true. n_neighbors strongly affects local structures. But the global structure is built from how the local neighborhoods are linked together. Changing the local connections always changes the global picture. Even if your data is already easy to separate, the algorithm still builds a graph based on nearest neighbors. The graph's structure, therefore, gets affected by changing _n_neighbors . The algorithm doesn't ignore the graph just because the data is simple to separate. This is the overall theme, exploring how the parameter _n_neighbors impacts the results from spectral embedding, a dimensionality reduction technique. We're focusing on understanding the effect of this key parameter. I start with a dataset. Think of it as a collection of points, each with many characteristics. For example, it could be information about houses, like size, number of bedrooms, and location, each house representing a point. From the KNN graph, I create a Laplacian matrix. This matrix describes how the points are connected in the graph. It's key to spectral embedding because it captures the relationships between points in the data. I decompose this Laplacian matrix. It's like finding the hidden building blocks of the matrix, which will help me to project my data into a lower dimension. Using the results of the eigenvalue decomposition, I create a lower dimensional representation of the data. Think of it as projecting a 3D object onto a 2D surface, but in a way that preserves the important relationships between points. This is the final output of spectral embedding. The output is the lower dimensional representation of the input data, a much smaller dataset preserving the relationships between points as much as possible. I construct a k-nearest neighbors graph. I'm looking for nearest neighbors based on distance metrics, like Euclidean. The parameter _n_neighbors controls how many neighbors I consider for each point. A larger _n_neighbors value means I connect each point to more of its neighbors, resulting in a denser graph. A smaller value leads to a sparser graph. This choice affects how the points are connected in the graph, and therefore directly impacts the final embedding. It's crucial. This question explores how changing the _n_neighbors parameter affects the output of the spectral embedding algorithm. It's all about understanding the role of this parameter in building the underlying KNN graph and how this influences the final embedding. The whole process involves taking data, creating a graph based on neighbors, calculating a matrix representing those connections, decomposing that matrix, and finally producing a lower dimensional version of the original data. The impact of _n_neighbors is a central focus here. I am exploring how this single parameter affects the shape and structure of the final output of the spectral embedding algorithm. I'm asking you to identify which statements correctly explain how changing the number of neighbors considered in the spectral embedding algorithm affects the results. This algorithm uses a graph to represent your data, and the number of neighbors influences how this graph is constructed and, consequently, the final output. It's a bit like deciding how many people you want to consider friends to build up your social network. More friends, a more connected network. Fewer friends, a smaller, more close-knit group. I've noticed that when you increase the number of neighbors, the resulting data visualization becomes smoother and shows a clearer overall pattern. Think of it like increasing the resolution on a blurry image. You start to see more detail and a clearer overall picture. I've found that using fewer neighbors means the computer needs to do more calculations, and this takes longer. It's similar to trying to find the shortest path between cities on a map. Using fewer connecting roads, neighbors, requires checking more possibilities to find the optimal path. It's more computationally intensive, not necessarily in a drastic way, but it increases with the number of data points. I'm observing here that the choice of the number of neighbors affects the local relationships significantly, but that effect extends to the global structure, which is inaccurate. The global view depends on how the local clusters are connected. I've noticed that even if your data points already form a nice straight line, linearly separable, the way you build the connections still matters, and using a different number of neighbors results in different visualizations. This is the overall framework of the spectral embedding algorithm, and the number of neighbors is a critical parameter in this process. The input to the spectral embedding is high-dimensional data. Spectral embedding is used to reduce the dimensionality of high-dimensional data. This step builds a graph representing the relationships between data points. The n_neighbors parameter dictates how many nearest points are considered when creating connections in the graph. K represents n_neighbors here, implying that for each data point, we find K nearest neighbors. This graph forms the basis for the rest of the algorithm. A matrix representing the graph is created, using the adjacency matrix of the KNN graph generated earlier. The Laplacian matrix is calculated from this matrix and is used to reflect the relationships between data points in the graph. A Laplacian matrix is a type of matrix used to represent the connectivity of the graph, and its calculation depends on the graph structure generated in the previous step. This involves performing an eigendecomposition of the Laplacian matrix, finding eigenvectors and eigenvalues. The eigenvectors will reveal information about the structure of the data, forming the basis for the low-dimensional representation. The output is the low-dimensional embedding of high-dimensional data. The eigenvectors from the spectral decomposition are used to create this lower-dimensional representation of the data. I see spectral embedding as a method for simplifying complex data. Imagine you have a tangled ball of yarn. That's your high-dimensional data. Spectral embedding helps you untangle it, creating a clearer, lower-dimensional representation while trying to preserve the essential relationships between the different yarn strands. It uses a clever mathematical trick involving a matrix called the Laplacian, derived from a graph representing the data's structure. The goal is to find the best way to lay out the yarn in a simpler, lower-dimensional space. To begin the entangling process, I first need to create a graph. I'll use a k nearest neighbors, KNN, graph. Think of each yarn strand as a data point. For each strand, I find its k closest neighbors, that's the k in KNN. I then connect each strand to its neighbors, creating connections within the tangled ball. The number of neighbors, k, is crucial. More neighbors create a denser graph, more connections between strands. Fewer neighbors mean fewer connections, focusing on localized clumps within the ball. The parameter n_neighbors in spectral embedding controls this k value. It's like deciding how tightly I want to weave the yarn together before I start entangling. Now, with the yarn connected into a graph, I compute the Laplacian matrix. This is where the math gets a bit heavy, but the core idea is that the Laplacian captures the relationships between different yarn strands based on their connections within the graph. It describes how the strands are interwoven. A dense graph, lots of connections, gives you a different Laplacian than a sparse graph, few connections. This matrix is key for the next step. Finally, using the Laplacian, I perform dimensionality reduction. This is the actual entangling. I use the Laplacian's properties to find the best way to lay out the yarn strands in a space with fewer dimensions. The result is a simpler representation of the data, where the key relationships are maintained, to the best of my ability, while reducing complexity. It's like taking the tangled yarn ball and skillfully spreading it out on a flat surface. This question focuses on understanding how my choices in Step 2, KNN graph construction, impact the final outcome. In essence, it asks how the number of neighbors considered affects the final untangled layout of the yarn. This statement is about the effect of having more connections in the yarn graph on the final layout. If I use a lot of neighbors, a large K, I get a smooth and well-connected final layout. This option focuses on the computational time. Finding fewer neighbors for each strand is faster, thus decreasing n_neighbors speeds up calculation. This is assessing how the number of neighbors affects the overall structure of the final layout. This addresses the impact when the data is already simple, whether the number of neighbors would even have any influence.